Okay, the next 5 problems are just mixing up all the different kinds of problems, or some of the different kinds of problems that we've used over the last few laws. Good news is that we really only have these 3 formulas that we need to use. This formula can be manipulated to apply to all the formulas. So to Boyle's when we don't have the temperature, to Charles when we don't have the pressure, and to Gay-Lussac when we don't have the volume. So all of this can be used. That's the good news. You only have to use that one and manipulate. Let me show you what I mean. And then when it says collected over water, remember we're going to use this chart here, we need a chart, but we're going to use that chemical or that algebraic formula. Goodness, that algebraic formula. Remember, these two are really the same. This is just very specifically 2 gases inside the container, water vapor and the dry gas. Sometimes this says dry gas, and I think that's what it says at the top of your worksheet. Okay, as we look at this first problem, we see that we are finding the new volume, so we're looking for volume. We know this is a volume, so this has to probably be my V2 if it's a later volume. As I read this, these are my 2 temperatures. So pressures remain constant, so I think about the formula V1 P1 T2 equals V2 P2 T1, and then I look at my numbers and I say I don't have any pressures, or I don't have 2 or need 1, so whatever I have 2 of, or have 1 and need 1 of, is what I'm using. So what I'm saying here is that I do not have any pressures. So that would be crossed out. And now we have Charles' law. Not that you need to know that, but that's the formula that's left on the screen. So then we can use this without the pressures because there is no change in pressure needed or given. So then we're going to put in our initial volume, 551.87 milliliters. I've already converted both these temperatures over before I set this up. So this one was 285.63 Kelvin, and this one was 329.37 Kelvin. Let me try that again. 329.37 Kelvin. This is a 9. Okay, so I convert that. So now I'm going to carefully plug in my T2. So 285.63 Kelvin. This is supposed to be a K. My writing was too sloppy. Okay, equals V2 is what we're solving times T1. So 329.37 Kelvin when I converted those into Kelvin. So now we're going to multiply 451.87 times 285.63, hit equals, divide by 329.37, and we get a volume of 391.86 milliliters. Okay, for our second example, we are going to look what we're solving for. We're looking for dry gas, the pressure of the dry gas. That's a little bit of a giveaway, that we are going to need to use the formula that is P total equals P water plus P dry gas. In order to use this, anytime we see collected over water, we have to use a vapor pressure table. So we're going to go look at the vapor pressure table. I'm going to insert that in here. I'll be right back. Okay, because it says collected over water, we know we have to use this vapor pressure table. This vapor pressure table is on the Dalton 1 worksheet. It also is on your formula page that you have that you got at the beginning of first semester. We need to use this table by looking at the temperature. So whatever temperature the water is collected over, we find that, which is right here, and then we have the pressure of the water at that temperature. So right now then we have to continue to read. I know that the pressure here is 5.6. The unit is kPa, but let's see what else we have in this problem. So because it says collected over water, we have to use the vapor pressure table. I've talked to you about how to use that. And now it says that the volume of the gas is 78.14 milliliters, so this is a volume. And the pressure of the gas is this. What is the pressure in kPa of the dry gas? Okay, so we have only 1 T, so we're not using T. We only have, better said, we only have 1 T or need 1 T, so we aren't going to have temperature used in this example. We only have 1 volume or need 1 volume, so we won't use volume. So by default, we know that we're going to go back to the Dalton formula. So if we don't have temperature and volume that we have or need 2 of, then we know we're going to default back to just Dalton's law. So we're going to take our total pressure, which has to be the pressure we're given, 87.68 kPa, equals the pressure of water, which is 5.6 kPa. We got that from the chart. Will give us the pressure of the dry gas. So we're going to take 87.68 and subtract 5.6, and we should get our P dry gas to be 82.08 kPa. So again, we did not have to do the V1, P1, T2, V2, P2, T1 formula because we had no change in temperature or pressure that was either given or asked to solve for. So by default, then we know we're using the Dalton's law formula as I described here. Okay, looking at 23 from the notes, it might be numbered slightly different, but that's because this is an updated version of the notes. As I read this problem, I know I'm looking for the final pressure, okay, and I see that the balloon goes from this temperature to this temperature. So by the way that's read, that 65.13 is T1 and 2210 is T2, and it tells me my initial pressure is this. So that is my P1 because it says it's the initial pressure. So therefore, I'm solving for P2. We already knew we were solving for a pressure, but as this word problem reads, we know we're actually solving for P2. So our formula is V1 P1 T2 equals V2 P2 T1. And I know that in this problem, I have only pressure and temperature, so I do not need volume. There's no change in volume, either given or requested. Therefore, I know that I can eliminate that. So this is Gay-Lussac's law. You do not need to know which law this is, but if you understand that you can always put the combined gas law formula down and then eliminate pieces if necessary, you get the other laws. So now I know my formula is P1T2. So 0.90126 ATM times T2. I've already converted those into Kelvin. When I did the problem in my practice, this was 295.26, and this one was 338.29 Kelvin. So my T2 is the 295.26 Kelvin equals P2, which is what we're solving, times T1, 338.29 Kelvin. Just like we've always asked ourselves, what do we have two of? We have two temperatures. They're in the same unit, so we're done. We can do the math. So I'm going to multiply 0.90126 times 295.26, hit equals, divide by 338.29, and I get an answer of P2 is equal to 0.7866 ATM. Okay, on this problem, we are looking for volume. Label things as we go. I have a pressure, a temperature, and a volume here, and I have STP, so then I have a temperature and a pressure without getting a temperature and pressure numerically. It looks like I have, this would be a P1 and a T1 and a V1 because those all occur at the same moment. Therefore, by default, this is P2, T2, V2, T2, and P2. So my formula is V1, P1, T2 equals V2, P2, T1. I have changes or need changes in all three, so I must keep the combined gas law written like that. I'm going to do 1.368 liters times P1 is 87.31 kPa times T2. T2 is standard. Remember, standard temperature is 273.16 Kelvin. V2 is what we're looking for. P2 is standard. And in this case, we're going to do 101.325 kPa because we might as well pick whichever standard helps us to do less math. And we would not want to convert, most likely. And then our standard temperature, excuse me, and our T1, not our standard was T2, but our T1 was 8312. 8312 is converted into Kelvin as 356.28. Okay, so now we're going to multiply 1.368 liters. Oh, before we do that, we need to check, what do I have two of? I have two pressures, they're in the same unit, so I can do those. I also have two temperatures, they're in the same unit, so I can do those, use those. So nothing to convert, everything's in like units, so I can just go ahead and do the math. So 1.368 liters times 87.31 kilopascals times 273.16 Kelvin equals, and then divide by 101.325 kPa equals divided by 356.29. That's supposed to be a 29. Oh, nope, that is a 28. That's a 28. Anyway, so when you do that math, you're going to get somewhere near 0.9038 milliliters. So 0.9038 milliliters. Okay, as I look at this problem, I see the word partial pressure. That is a giveaway. Or you could see more than two pressures, so that's also a giveaway, that we're going to do P total equals P 670 plus P 891 plus P 856 plus P 665 plus P 134. So I had to account for all of my gases, because remember Dalton's law says the total pressure inside the container is equal to all the pressures of the individual gases inside the container. As I read this, I see that I have 987.1 millimeters of mercury for my total. It says total pressure right there. 760 is 0.6012 atm. Pressure of gas 891 is 27.64 kPa. The pressure of gas 856 is 97.23 torr. The pressure of gas 665 is 3.171 kPa. And then we're looking for the pressure of gas 134. That's kind of hidden. It's right in the beginning, so you have to be careful. That's what we were solving for. Okay, so now before I can do any of this, I have to have all units in the same. All these pressures have to be in the same. I'm going to go to millimeters of mercury just because it's the start. This is really easy because it's a 1-to-1. We already know this is already, can be easily converted. The rest of these will require some grids. So we're going to start with this one right here and get it into millimeters of mercury, 0.612 atm. We know 1.00 atm equals 760. Remember, we're getting all to mmHg. That value is 456.91 mmHg. So I'm going to change that out to be 456.91 mmHg. And then I'm going to convert this one, 27.64 kPa. We know there are 101.325 kPas for every 760 millimeters of mercury. So let's see if I can make this. I don't know why this part of my screen is being sensitive, but it is. It's 27.64. Maybe it's the user. Okay, so 27.64. I'm going to get to 207.32 mmHg. These should be this should be a review for you. We've been doing this throughout this whole unit. So that's going to make this go to plus 207.23 mmHg plus 97.23 mmHg plus, I need to convert this last kPa number, so 3.171 kPa. I know there's 101.325 kPas for every 760 millimeters of mercury. When I convert that, I get 23.78 millimeters of mercury. So this is going to be 23.78 millimeters of mercury. Let me make that a little more legible. And this is kind of hard to read too, so let's fix that. apologize. It's just... Okay. This was a 97. I'm just going to make that a little cleaner. All right, so now we can do the math. So all of this is addition. So we're going to take 987.1 millimeters of mercury and subtract all of these. So you can either add all these up and then subtract them over. I don't like to waste all my time doing that. I literally just start punching into my calculator. Up to you. 987.1 minus 456.91. This was a 6. Hit equals minus 267.23. Hit equals minus 97.23. Hit equals minus 23.78. Hit equals. So our P 134 has a pressure of 202. Criminy. I don't know why this part of my screen is not working. 202.58 millimeters of mercury. Okay.